Let me give you some examples of white dwarfs. This is a binary star system consisting of a star called Sirius, or Sirius A, because there are two of them. It is the brightest star in the sky that we can see. It's at about 8.6 light years away from us, and its luminosity is about 25 times larger than the luminosity of our sun. Its mass is about twice, but because luminosity scales with the mass as mass to the power 3.5, turns out that it's 25 times more luminous. And it is a normal main sequence star. But you can see here this bright dot, its companion, Sirius B. It is a white dwarf. Okay? And this image was obtained using the Hubble Space Telescope. Okay, so this image was obtained in 1995, again using the Hubble Space Telescope, and it was a research project led by Canadian and American astronomers. They focused on a particular segment that you can see here of a cluster M4. And this is the blow-up of this small region that you can see here. And all these little bright things that are circled are white dwarfs. And the rest, of course, are main sequence stars, either sun-like or red dwarfs. Okay? So these things are not something that exists only in theory, but actually they have been observed. Now, this object, a white dwarf, that is the dead core of a medium mass star, is extremely dense. It's been compressed through these final stages of star's evolution, so it has a very large density. And the density of white dwarf is typically about 1,000 kilograms per centimeter cubed. Compare this to the density of water, which is 1 gram. And 1 gram is 1,000th of a kilogram. So it's 1,000,000 times smaller than the density of water under normal conditions than the density of a typical white dwarf. So they are extremely dense, they are extremely heavy, and the question is, if they are not producing energy anymore through the fusion, how come that they don't collapse under their own weight, under their own gravity, right? What is holding them up? They're so dense that you would think that the gravity would win and would collapse the whole thing, but it doesn't. So the question is, what is propping up a white dwarf? Okay, so it turns out that it is supported against gravitational collapse by so-called electron degeneracy pressure. Okay, let me make a schematic diagram of a white dwarf. It consists of positive carbon nuclei and some oxygen nuclei. So we have, which are densely packed. There are many of those. Okay, so what we have here are positively charged carbon and some oxygen nuclei densely packed. But of course the object has to be electrically neutral because if it wasn't, then all these positive charges would repel each other and the whole thing would explode. Okay? So they are in a soup of electrons that carry negative charge, and make the whole object electrically neutral, okay? So I've indicated few. These electrons are in so-called degenerate state, and it turns out that in such state they have interesting properties that are consequence of the laws of quantum mechanics. Electrons obey so-called Pauli principle, and what it says is basically, in addition to their spatial degrees of freedom, electrons also have a magnetic moment which is associated with intrinsic property called spin. And it turns out that that magnetic moment can point either up or down, okay? And what Pauli principle tells us is no two electrons can be in the same state, which includes their spin, okay? So for example, if this was a given spot in space, in that spot I can put only two electrons, one with its spin or magnetic moment up, and another one with its magnetic moment or spin down. Okay, so to see the difference between degenerate and normal electron behavior, I want to make the following analogy with a parking lot. So suppose we have a parking lot with parking spaces, and there are only few cars parked. If the new car comes in, the driver can drive slowly because he can pick his parking spot. Okay? So this would, what I would call, that would be, this would correspond to the normal electron state. Now the degenerate state would correspond to the opposite case when we have only very few parking spaces available, okay? And there are only few spots left, okay? So then the cars that are coming, drivers are moving fast because they are racing to find the parking spot. So that would be degenerate state of electrons. Because of the Pauli principle, they can only fit in these slots, okay? And because the electrons in the degenerate state are moving fast, they are creating that additional pressure, not the thermal pressure, but that's purely quantum mechanical effect that actually supports the white dwarf. That's why it does not collapse.